Hi students, Charlie Busso. I'm back. 2021. It's New Year's Day. And we're going to do a short Zoom to explain some of the vocabulary and look at some of the graphs that we're going to need to know about in what's called phases chemistry. This is about stuff, matter, changing phases, figuring out what phase it would be in at a certain temperature and pressure, but also what happens during a phase change. It's a physical change, but stuff happens that we can explain from a chemical or particle point of view. Um, this is short. This is important. This is not in the notes. This is just getting to know you kind of stuff. Phases chemistry. So here we go. Matter comes in different states or different phases. There's obviously three phases: solid, liquid, and gas. All substances can be solid, liquid, or gas. A lot of things like to be solid because it takes a lot of energy to shake them up, loosen them up before they turn into a liquid. Metals, for instance, are all solids at room temperature except the best element, mercury. Obviously, solids have certain properties. The particles are organized. Look at this picture. The atoms here are organized in a rigid pattern that does not change. It's very, very constant and steady and orderly. It's very dense. The particles don't squish because they're really so close together. But if you shake them up enough, if you heat them, usually that's enough. If you heat them enough, you can break free the bonds that are holding it together as a solid, and they become looser and they start to move on each other. This middle diagram for a liquid, this diagram shows that the particles are not orderly. That's a really important point. They're still pretty closely packed. You can't squish liquids very much, but they're not orderly, and they are moving. They are literally moving all around. The glass of water looks like it's very still, but the molecules inside are moving around quite a bit. The last one, we have to even draw little arrows on them to show that the particles are all moving in many different directions at the same time, and they will bounce off of each other, and they'll bounce off of the walls of the container they put them in. There's a very, very, very low density for gas. Okay, there's a lot of room. You can squash the heck out of gases, or you can expand them and they'll become less dense. Or if, for instance, they're perfume, you put a little spritz of perfume in a cup, you can smell it pretty well. But if you put a little spritz of perfume in the commons, you might not notice it at all because the gas has so much room to spread out. The molecule per liter would be so low, you might not even notice it. So solids, liquids, and gases are the three main phases. Of course, we have aqueous, and somebody's going to say something silly like, what about plasma? Don't worry about plasma. Aqueous just means dissolved in water. It's not really a phase, but I know it's got to go in here somewhere, but we're not talking about it right now. Now, one of the most important graphs is called the heating curve. Now, I know high school kids are looking at this like, oh no, a graph. I don't want to look at a graph. This is really important, and it's really simple. And if you just would let me explain this to you, you need to be able to look at a graph like this and get information out of it, or you can put information into it. Now, the most important thing, first of all, the title, it's called the heating curve. That means you're going to add heat. You're adding heat. You're not removing heat. This is called the heating curve. So stuff starts out really cold. If we look at the y-axis, the up and down, we start out not at zero. Not at 0 Kelvin anyway. Start out really, really cold, but not at 0. You can never be at 0 Kelvin. And that red line marked number 1, that means that you have a substance that you're going to add heat to. Look at the y-axis. It's called the temperature. And look at the x-axis. Heat is being added at a constant or uniform rate. You're adding heat constantly. Now, what happens when you have something that's really, really cold? It's probably a solid. And you start adding at heat at T0. That means time 0. And from time 0 to time 1, T1, you're adding heat at a constant rate. And what happens? The temperature goes up. You add heat to something and it gets warmer. So look at that red line, number 1. It starts out not at 0 Kelvin, but as you add heat at a constant rate, the temperature goes up. It goes up, it goes up, it goes up, and the solid gets hotter and hotter and hotter. But then it reaches what's called the melting point. The melting point, this is phase chemistry. This is an important thing. It's a phase change now. Watch what happens from T1, which is the melting point, the temperature where the solid becomes liquid. At T1, we keep adding heat at a constant rate all the way up to T2, but the temperature is not going up anymore. Right? From T0 to T1, as we add heat, the temperature goes up. That makes sense. We're adding heat and stuff gets hotter. The particles of the solid shake faster and faster and faster, and they vibrate more, and they actually increase in temperature. But at T1, which represents the melting point, the temperature where the solid begins to turn into a liquid, from T1 to T2, that's the melting point, temperature does not increase. Now that makes sense because things have a melting point. What is the melting point for H2O? Well, ice melts into liquid water at 32 Fahrenheit, which I don't like to use, 0 degrees centigrade or 273 Kelvin. That's the melting point. That's the temperature. There's only one temperature. It's the melting point. So the temperature from T1 to T2 is constant. But how weird is it that we're adding energy, but the temperature doesn't go up? Think about this. The solid during the red line, number 1, the solid is vibrating and vibrating and vibrating faster and faster, and it's going to get warmer and warmer and warmer until it reaches that special temperature called the melting point, where it begins to actually break apart. And at T1, at the blue line, that's where all the energy going in no longer increases the temperature. All of the energy is used to shake the solid apart into a liquid. And at T2, at the end of the blue line for number 2, that's when all of the solid has become a liquid. And once it's all a liquid, any more energy you begin to add at T2 makes the temperature go up. So on section 3 of the graph, we are above the melting point, makes it a liquid, and it gets hotter and hotter and hotter and hotter and hotter. We add energy at a constant rate. It gets hotter and hotter and hotter until it reaches the end of that red line 3, which is called the boiling point. Now, at the boiling point, there's one temperature where the substance goes from the liquid to the gas phase. And at T3, that is the beginning of the change. At T3, on the red side of T3, the red line going up at temperature 3, that's as hot as a liquid can get and stay liquid. If it gets any hotter, it can't get hotter. If you give it any more energy, it's going to blow itself apart into a gas. All the energy goes to phase changing. Section 4 of the graph, the blue line that goes across on the top, that's the phase change from liquid to gas. At the end of the blue line, at T4, that's where all of the liquid is blown apart into the gas phase. And when all of the liquid becomes gas, if you can still add energy, you can make the gas particles move faster and faster, and you can get hot gas. You have cold gas, medium hot gas, or really hot gas. And if you bring it to the sun, you can make a super hot gas. All right, so the heating curve shows all of the different phases and all of the, hold on 2 seconds, get out of this room, please. My son is teasing me. And now he's in the video. He thinks he's bothering me, but my son Charlie was acting kind of goofy, and now I'm putting him in my video. This next slide shows the heating curve for water. Now, you're very, very familiar with water. We're going to start right back at T0 again. It's the same exact graph, actually. But at T0, which is not 0 Kelvin, it's just really super cold, you have solid H2O. And as you add heat from T0 to T1, the ice gets warmer and warmer. Now, that makes no sense, but think about it. You live in a very easy world. You live in Vestal, you have ice in the freezer, you have ice outside, and it melts. But if you had ice in your freezer, it would be what, -5 degrees centigrade? What if you had ice in Antarctica? It might be -25 centigrade. Hold on 2 seconds. Please be quiet. It could be -25. Now, if you brought that ice from Antarctica to Vestal, and put it in your freezer, it would stay frozen, but actually it would warm up. You can make ice really cold, or you can even have warmer ice. You can have ice closer to the melting point, still frozen, but warmer than really cold. So from T0 to T1, the ice is warming up. You're shaking that ice, the particles, the molecules of water that are stuck together start vibrating and vibrating and vibrating, but at T1, at the melting point, it starts to break apart. And as you add heat, you do not increase the temperature, which is weird because it's a phase change. And as the heat is added, the solid becomes a liquid. And it stays a liquid until all of the ice is melted into water at T2. At T2, when all of the H2O is in the liquid phase, you can warm up the liquid and it gets warmer and warmer. We keep adding heat and it gets hotter and hotter and hotter and hotter until it reaches 100 centigrade or 373 Kelvin, which is called the boiling point at T3. Now at T3, at the boiling point, that's as hot as liquid water can get and stay liquid. You add so much energy, the particles moving so fast on each other, but they're still able to stay stuck together, right? They're still able to stay liquid and not blow apart. But if you add even a little bit more energy, they can't get hotter, they begin to break apart. And it starts to flatten the graph out because at the boiling point, that's as hot as liquid can get. Now for water, the boiling point's 100 degrees centigrade. Water can't get hotter than 100 degrees centigrade. If you try to make it hotter, it turns to gas faster. It doesn't get hotter. Until the end of the blue line at T4, when all of the liquid is turned into gas, into steam, and then once the steam is at T4, if you can keep adding heat, if you have the ability to keep adding heat, the steam can get hotter and hotter. This heating curve is exactly the same as the generic heating curve we just looked at. The only thing different is in the title. It's not heating curve for any substance, it's the heating curve for a substance, which is water. And on the y-axis, we don't have melting point and boiling point. We actually have the temperatures that we know are the melting point for water and the boiling point for water. But if this were, for instance, the heating curve for gold for my ring, now gold doesn't melt at 0 degrees centigrade. It certainly doesn't turn into a gas at 100 degrees centigrade. But the graph's going to look the same. The solid's going to get hotter and hotter and hotter till it melts. Then the temperature gets flat. Then you're going to warm up the liquid hotter, hotter, hotter till you can't make it hotter and it gets flat because it begins to turn to a gas. And once my ring turns to a gas, which would be so sad for me, if you could keep adding heat, the gas gold could in fact get hotter and hotter. This graph is the same graph for every single substance. The only difference is what is the melting point and what is the boiling point and what's in the title. Now the opposite of this is called cooling curve. Here's a cooling curve. Now we're going to start out at T0, and this curve goes down. Cooling, we're going to be removing energy. It's going to get cooler, downward. We're going to start out at some crazy high temperature. I don't know how hot it is. Look, there's no temperature. See at T0, we don't know where the red dot crosses the y-axis. It's I don't know, freaking hot. As you remove energy, the gas is going to get cooler and cooler and cooler until the particles slow down, slow down, slow down. And at T1, they reach that temperature, the opposite of the boiling point. It's called the condensing point. And at that point, the gas begins to collapse into a liquid. And all across T2, up till temperature 2, all across the blue line 2 to T2, the gas is becoming liquid. At T2, this substance becomes all liquid. And if we continue to remove heat, we go down the slide number 3, and that makes it a colder liquid, colder liquid, colder liquid, till it gets so cold at T3, that's as cold as a liquid could be before it begins to turn into a solid. If you remove any more energy, you can't lower the temperature, the liquid can't get colder, but it starts to turn into a solid. And across 4, from T3 to T4, that's where the liquid becomes solid. At T4, it's all solid. And then once you have solid substance, the lowest energy substance, you can remove energy and make it colder and colder and colder, and it can get as cold as you want, but it can't get to 0 Kelvin. Nothing gets to 0 Kelvin. So this is the generic cooling curve. It's the opposite of a heating curve. It's exactly the same upside down. Now watch this. We have a cooling curve here for water. You know about water. Imagine some really, really hot steam. I don't know how hot it is. Pick a number. It doesn't matter. It's got to be 173 Kelvin. I'm sorry, 173 centigrade. 185, it doesn't matter. Some really hot temperature above the condensing point. And as you remove energy, that steam actually, the particles slow down. They're not moving so fast. They don't have so much energy. The temperature drops. And it drops and drops and drops until it hits that special point called 100 degrees centigrade, which is what's called the condensing point. And at that point, T1, the gas begins to turn into liquid. All the way across that blue line, the gas becomes liquid. At T2, all of the steam is gone, and now we have just liquid H2O. And as we continue to remove energy and go down that red slide, the liquid water starts out really hot, 100 degrees centigrade hot, and it gets colder and colder and colder and colder. And if we keep removing energy until it hits 0 centigrade, and at 0 centigrade, that's as cold as liquid water can be and stay liquid. But if we remove any more energy, the liquid is moving so slow now that the particles are actually attracted and locked together, and it begins to turn into a solid ice cube. And going across the blue line there from T3 to T4, that's where it becomes completely solid. At T4, our H2O is now an ice cube. It's a warm ice cube, but it's an ice cube, solid. And as you remove energy, it gets colder and colder and colder, and you can make it as cold as you want. You just can't get to 0 degrees Kelvin. So we have heating curves for everything and cooling curves for everything. All the cooling curves look exactly like this. The only difference between a cooling curve for water and a cooling curve for gold, say, is the title. And what is the condensing point and what is the freezing point? You have to look those up. But the picture looks the same. The phases stay the same. The shape, the down, the flat, the down, the flat, the down. They're all exactly the same. Temperature decreases on the y-axis and heat's being removed at a constant rate over time on the x-axis. Every cooling curve looks just like this. The only difference is the tidal and the actual temperatures. Now, this is a weird concept. It takes a while for teenagers to ever understand. If you had two exact same beakers at about 25 degrees, they're the same temperature, whatever it is, room temperature, and you have water in the blue one, and the other one is called nail polish remover, which technically is called acetone. It's an organic molecule. Now, if you put both of these glasses on the table in the classroom, they both start to evaporate. But water doesn't evaporate so well, right? It's going to take many hours for the water to evaporate. You know, you have a glass of water, you leave it out overnight. You don't drink it. Sometimes 2 or 3 nights, you leave it on your dresser. It's still there. It takes a while to evaporate. Water doesn't evaporate very well. But acetone, acetone is also called nail polish remover. And I have only yelled at my daughter when she wants to take the nail polish off her fingernails, because when she uses this stuff, I think it smells terrible. And because it evaporates so easily, it gets into the air. I mean, it takes a nail polish off, right? It gets off her fingers, but it also evaporates and I can smell it. Sometimes she's in the basement. I'm like, Sophia, what are you doing? Nothing, Dad. I'm like, are you doing your nails? I always have to yell at her. She always seems to forget that I'm going to know. Sometimes she's in the garage. I'm like, what are you doing? Nothing, Dad. Take that in the yard. I can't stand the smell. Now, liquid is not liquid. All liquids are different. Water evaporates slow because the molecules are very, very attracted together. And that holds them together and makes them harder to come apart. Nail polish remover molecules, acetone molecules, are much less attracted together. So when you have a glass of nail polish remover, a beaker of it, say, it doesn't stick together so well. So at the same temperature, it evaporates much faster. And it happens to smell. And it gets into the air, and I can smell it, and I get all grumpy. So when you have two different liquids, sometimes they evaporate slow or fast, depends on what they are. And that has to do with what molecules are they, and how much attraction do these molecules have to each other. The stronger the intermolecular attraction, the worse they evaporate. The weaker their attraction, the easier it is to evaporate, right? Now, what if we took a glass of water and put it inside a big glass bell jar, they call it. We have a nice flat rubber top. We put the beaker on it, and we put the glass bowl over it. Now outside, there's air pressure, like there's air pressure here, and there's air pressure inside the bowl. When I put that big bowl over the top of the beaker, there's air pressure inside. It's the same. It's based upon the air, how much air. It's the same air when you put it on nice and slow. You're not capturing extra air in it. It's air pressure in there, air pressure outside. It's the same. But what happens once you seal it, once you make what's called a closed system? Inside the beaker, inside that dome, in the beaker is the water. The water is whatever temperature it is outside. Now, water doesn't evaporate so well, but it does evaporate. The temperature of the room, say it's room temperature, 25 degrees. That's not very warm for water. And water sticks together pretty well. But inside this closed dome, extra molecules of H2O are going to evaporate, and there's going to be more particles in that space, and they're going to have more collisions because there's already air in there colliding, creating some air pressure. Now you have extra water in there. There's going to be extra pressure inside of this closed system that's caused by the evaporation of this liquid. Now that extra pressure, the difference between the outside air pressure and the inside air pressure, the inside the dome also has this extra pressure caused by extra molecules from evaporation. That's called vapor pressure. And that's a way to measure how well does something evaporate. If it has a low vapor pressure like water, inside this tank is not going to be much more pressure than outside the tank. It's never going to explode, right? We don't have to worry about so much gas is going to evaporate from the water that it's going to explode because there's so much more pressure. That's because the water doesn't evaporate too well. And because it's a closed system, not only does it evaporate, some of it bounces back into the water by mistake, and it kind of recondenses. So at some point, it's going to become steady pressure. There'll be a certain amount of evaporation and a certain amount of condensation. But the extra difference is called the vapor pressure. Now, if you have a low vapor pressure, like water generally is a low vapor pressure, it's because water doesn't evaporate well. But if we had the exact same setup, but instead of water, we had a little glass of acetone in there and gave it a little time, the acetone evaporates so much more, there's going to be more acetone molecules inside that dome. There's going to be more collisions, there's going to be more pressure. The pressure in there would have a higher pressure reading because the acetone evaporates easier. So if you evaporate easy, you have a high vapor pressure because you evaporate more and you get caught in this closed system, and you end up having more collisions with all the other gas molecules, and you're banging around in there, and there's more particles, it's denser, right? Now, vapor pressure in the bottom, the very bottom in black here, it's affected by two things, temperature and intermolecular attraction. Now, temperature, if we had two of these and one was cold and one was hot, the hotter one is going to have a higher vapor pressure because if you have hotter water or hotter acetone, it's going to evaporate more because the particles will be moving faster and faster, and they'll jump out of the liquid phase quicker. But also it matters acetone to water, say. One, the water has very strong intermolecular attraction. It's going to have a lower vapor pressure, whereas acetone, which has very weak intermolecular attraction, is going to evaporate quicker. It's going to have higher. So there's two things that affect what's called vapor pressure. Temperature, hotter usually increases the vapor pressure almost always, and the intermolecular attraction. The stronger the intermolecular attraction, the lower the vapor pressure. The weaker that attraction is, the easier it evaporates, the higher the vapor pressure. Okay, one more slide. This is going to be a picture from table H. Now, table H is one of the hard things to see. This is what it looks like. There's four curves. This curve is just the water curve. See the third one? It's called water. You should get a good look at this. This blue curve, that's just the water curve. It's from table H. There's three other curves on table H. This is just one. You can only look at one curve at a time anyway. Now, there's a couple of things. The vapor pressure goes on the y-axis up and down, and the red dotted line right down the middle is a dotted line on table H. That is called standard pressure. Now, I know you don't understand the units. They're called kilopascals. Don't worry about that. We'll get to that. That's not important. It's just a unit. But at some point, there's what's called standard pressure. That's like normal, average, the same. That's what we call standard pressure. Across the bottom is the temperature. Now, we're going to pick 50 degrees because it's in the middle of the graph. If you would, this table 8 shows a lot of things. I'm going to try to remember to show them all to you now, but we'll get to all of them. If you were to go to 50 degrees, now 50 degrees centigrade is pretty damn hot, way hotter than the July in Vestal. But at 50 degrees, if you run your finger up to the water curve, you're only up. Can you see where I'm pointing? You're only up just above the first box, right? Just above, and that gives you about, what, 11 or 12 kPa. On my graph on the slide, it's 12 kPa. Now, kPa is a really small unit of pressure. Don't worry about what it means. It's just a little unit. It takes 101.3 to be normal. So 12 kPa. What does that mean? That means if you heat water up to 50 degrees centigrade, which is too hot to take a bath in, it would burn your skin. It's that hot. But it's not boiling, but it's uncomfortably hot. That temperature for water that has pretty strong intermolecular attractions, you're only going to get 12 extra units of pressure in a closed system. It's not very much, right? So this graph tells you, hey, if you heat your water up to 50 degrees, you're going to get this extra pressure, right? Also, if you heat it up to, say, 70 degrees, let's see, it's not on my slide, but we can look at this picture. If we go to 70 degrees and we go up to the water line, now we're up to 30 kPa. So if we had a closed system and we heated it up with water inside up to 70 degrees centigrade, which is really pretty warm, way too hot for people, cooking temperature almost, we're going to have 30 kPa. That means the water is going to evaporate that much more, almost triple what we had at 50. And if we heat it up to 100 degrees centigrade, which is the boiling point, we're going to get 101.3 kilopascals, units of pressure that's going to come out, which actually equals air pressure. So this shows, this curve tells us at any temperature how much extra pressure is caused by the evaporation of a liquid. Now, ready for this? This is going to be really, really hard to understand, but really cool. This curve also represents the boiling point for water at any pressure. So let's start with 101.3 kPa. If we go right across the graph in the red dotted line, where does the blue curve cross that pressure? At 100 degrees. What does that mean? That means at normal pressure, water will boil at 100 degrees. When the vapor pressure matches the air pressure, that's going to be the boiling point. Now, I have a sister-in-law that I'm going to talk about in the notes. She's a witch. My wife's sister is a witch. Can't stand her. She can't stand me. She happens to live in Boulder, Colorado, right? Boulder, Colorado is way up in the mountains. I visited a few times. Beautiful. But you get there, you're just so high up in the mountains, the air is much thinner. There's much lower density because you're so much higher in the mountains. There's literally that much less atmosphere on top of your head pressing down. And it's beautiful. Now, in Boulder, Colorado, where the pressure is less than normal, the pressure is, let's say, I'm going to guess around 95 kPa. So if you were to put your finger at 95 kPa, you can't see it on the slide, but approximately, and roll it out to the water line and then drop it down, it looks like at 95 kPa, water would boil at about 97 degrees centigrade. That's colder than it would boil in Vestal. The water will boil at 97 degrees centigrade. Now, what if you went out, I don't know, let's say, kind of like to the space station. The space station. You tried to boil water on the space station. I can't even boil water. What if I'm an astronaut, I'm out in space, and I'm fixing the space station outside? First of all, I'd be way too afraid to get in a rocket ship. Right? I don't like that whole concept of shooting off a rocket ship. But imagine I'm outside, and a terrible thing happens. a little meteor comes by and rips my spacesuit open. I'm gonna die. Why am I gonna die though? Don't talk about me. The astronaut's gonna die. It's a shame. You see it in movies sometimes. When the spacesuit gets punctured, what happens? Well, they lose air, but you can hold your breath for 2 minutes, but they die faster than that. Why do they die? Because the pressure is so low. How low is it? It's almost zero, right? When the pressure suit busts open in space, all the gas rushes out. There's almost no pressure anymore. What if we went down to, I don't know, almost no pressure? Almost no pressure. What is the vapor pressure? What is the boiling point? The boiling point is 7 or 8 centigrade. You know what happens to a space person whose suit rips in space? All the water in their body boils. It doesn't get hot. You don't cook, but the water boils at a colder temperature because it's got a lower boiling point, and all the water turns to a gas, and they become freeze-dried. Scary to go in space. You got to be very careful. Table H tells us what is every single boiling point for water. That blue curve represents every single possible boiling point at any pressure, right? If you have low pressure, you have a low boiling point. If you have high pressure, you have a higher boiling point. If you have normal pressure, you get 100 degrees is the temperature. What if you had really, really high pressure? You know what a pressure cooker is? You get one of those big pots that the lid gets screwed and locked on. As you heat it up and the water boils and steam goes above and it can't escape, it pushes down. But as you keep adding heat, the steam holds it down, the water gets hotter and hotter, and the boiling point goes up. The water can get hotter and hotter and cooks faster because you can make water boil at a higher temperature if you have really, really high pressure. So if you had, say, 120 kilopascals, I know you don't know what the units mean, but if you were here, water would boil at about 105. And if you can make the pressure go up even higher, you can have even hotter. And the hotter the temperature of the water boiling, the faster your food's going to cook. So table H tells you every single boiling point of water at any pressure, or it tells you how much extra pressure is created by the evaporation of water at any temperature. It does 2 things at once. Table H is cool. Table H for happy. And it does it for 4 different liquids, water being the one you know. All right, I think that's it. This should give you a good handle. So once we get to the first slideshow and then the second, third, and the fourth, you should be doing much better at this. Phases are cool. There's so much going on, even though this stuff just changes phase. It's a physical change, but it's pretty cool. All right, welcome to chemistry. And I will end this meeting.